Hi, my name is Ashwani Kumar, and in this video, we are going to see the December 2019 UGC net questions on the second unit, that is VLSI or IC fabrications. So, coming to the first question here, we are going to see is in a MOSFET, the carrier density is scaled by. So, which of the options? So, generally, before going into the question, that you have to know the few points that in the MOSFET, we are having the two scaling factors, that is 1 by beta and 1 by alpha. And while coming to the 1 by beta scaling factor, we are going to use only for the two things, that is VDD, that is for the power supply, and for the what is called oxide thickness. Okay, that is silicon dioxide thickness. Generally, we will deal with respect to D, capital D, or for example, small t. Okay, so that means if you consider the MOSFET, here we are having the source and drain, and it is the gate, and this part is the silicon dioxide. So whatever the thickness of the silicon dioxide is there, that is I am representing with capital D, or else sometimes small t. Anything is fine. But they have to remember the what is the meaning of both these two. It is nothing but the thickness of the silicon dioxide, and a VDD is the power supply. So 1 by beta is useful for the scaling factors to represent the power supply and the gate oxide thickness. And while coming to the 1 by alpha is used for represent the remaining parameters, that is horizontal and vertical dimensions of the MOSFET, just like width of the channel or else length of the channel. So for any kind of things, we are going to take the we are going to take the scaling factor as a 1 by alpha. So both these 2 points are important. You have to know to solving such type of problems. So here they given that the carrier density. Generally, while coming to the charge carrier density, we are going to represent with rho, and where rho is equal to n into q. That means for n number of charge carriers, the charge density rho is equal to n into q. But here they simply represent the carrier density. So that's why here if I treated that n as a 1, then I will get simply q, that is charge. And this q can be taken as if you apply this formula, that means the voltage stored in the capacitor, the formula can be given as, why I am telling about the capacitor, because if you observe here, this is a polysilicon, and this part is acts like a gate terminal, and this is a silicon dioxide, and here it is a substrate, right? So the polysilicon is acting like a plate number 1, and the substrate acts like a plate number 2, and whatever the silicon dioxide is there in between both these two, it acts like a dielectric medium. Okay, so now this entire thing will just looks like a capacitor. So for the capacitor, the amount of charge stored in that capacitor for the given applied voltage. Why? Because for the MOSFET, let's take it is a source and it is a drain and it is a gate voltage, right? So for any don't apply this concept to this MOSFET right now. First, let's know about the basic concept regarding the capacitor. So if I took any one capacitor C, and that is connected to a battery with the potential difference V, now the amount of charge stored in this capacitor, that is Q, can be given as a V into C. So it is the formula to the charge stored in the capacitor. In the same way, the amount of charge or the charge density in this capacitor or else in this silicon dioxide, that is Q, can be given as V into C, where this V can be taken as a V suffix GS, that is gate to source voltage. Generally, we are giving the gate to source voltage as an input to the MOSFET into capacitance. Okay, that means the capacitance, whatever the formed here, the value of that capacitance we are going to take here. And this C represents the capacitance, so it can be taken as, generally C is nothing but the capacitance formula is epsilon A divided by D. It is the formula. And while coming to this capacitance, here we are going to take the COX, that is the unit area. That means the capacitance of the unit cross-sectional area. So unit cross-sectional area means A becomes is equal to 1. So epsilon divided by D. Okay. So where D is nothing but a distance between both these two plates. So distance between both these two plates is also nothing but a thickness of the silicon dioxide, right? So in this case, we can write that VGS into epsilon divided by capital D. So it is a Q, that is a charge density. So now if I apply the scaling factors to these parameters, anyhow the epsilon is a constant, so you need not to worry about that one. So here I am taking that the charge or charge density is directly proportional to VGS divided by D. And anyhow, while coming to the scaling factors, as I told that 1 divided by beta is the scaling factor we are going to use for the supply voltages, just like the VDD or VGS, okay, to the supply voltages. And 1 by beta is also used for the thickness of the silicon dioxide, okay, as we already discussed in the previous thing. So here the D is there, that means this D, whatever the thickness of the silicon dioxide is there, it is going to be scaled by 1 divided by beta, and whatever the VGS is there, it is also going to be scaled by 1 divided by beta. So now what I am going to do is that Q is equal to, in the place of VGS, I am substituting the 1 by beta, and in the place of D also I am substituting the 1 by beta. So actually after scaling, that if the initial thing is the VGS, then after scaling this VGS by beta, then we have to take the VGS by beta. Okay, but else you can just simply take, in the place of VGS, I scaled by 1 by beta, the thickness is also scaled by 1 divided by beta. Now both these two will get cancelled, then that becomes is equal to 1, or the charge density or charge is directly proportional or is equal to 1. So from this concept, here the correct option is the fourth option, that is the 1. It is a scaling due to the, scaling is applied to the carrier density of the MOSFET. And while coming to the next question, in a MOSFET, the gate capacitance is scaled by. So generally the gate capacitance CG can be taken as a epsilon A divided by T. So epsilon is a constant, so we are not going to scale this constant, so just leave about this one. So just focus only on the two parameters, those are other than the constants, that is A by D. And while coming to the cross-sectional area can be given as a length of the channel into width of the channel divided by thickness of the silicon dioxide. That becomes is equal to, here the length of the channel is scaled by 1 by alpha, and the width of the channel is also scaled by 1 divided by alpha. But while coming to the thickness of the what we call silicon dioxide can be scaled as a 1 divided by beta. So now it becomes is equal to 1 divided by alpha square divided by 1 divided by beta, that is equal to beta by alpha square. So it is the correct answer. So from this concept, the second one is the correct answer. And now while coming to the third question, question, third one, the power dissipation per unit area is scaled by. So that means in the given question, power dissipation per unit area, that means generally the power dissipation, generally the power formula can be taken as V square by R or else I square into R. So these are the power dissipation formulas. So in the V square by R, anyhow R is a constant, so don't bother about that one. And while coming to the V square, so V square is nothing but it is a power supply voltage. So the power supply voltage scaling is done by 1 divided by beta and whole square. That means the power supply, after scaling, we are going to take this parameter as a 1 divided by beta whole square divided by area, where area is length into width. The length is 1 by alpha, and the width of the channel is also 1 by alpha. So 1 by alpha into 1 by alpha, it is 1 by alpha whole square. So totally it becomes alpha square by beta square. That means the correct option for this power dissipation per unit area is scaled by alpha square divided by beta square is the correct one. And now while coming to this question, they are asking about the current scale density is scaled by. So generally the current density formula is I divided by A, and J is equal to, so I divided by A, and I can be written as V by R. So V divided by R into A. Anyhow, V is a power supply, so it has to be scaled by 1 divided by beta, and R is a constant, so just leave about that one. And area is nothing but, as I previously told that product of the length and width of the channel, that is 1 divided by alpha whole square. So 1 divided by alpha whole square. So it becomes as equal to 1 divided by beta into alpha square. So the answer is alpha square by beta is the correct thing for this current density. So alpha square by beta is the correct option. And now while coming to the next question, the saturation current is in MOSFET is scaled by. So if the MOSFET is in saturation, then the saturation drain current, that is ID, can be given as mu naught else mu COX W by L into VTD square. Okay. So why? Because if the MOSFET is in saturation region, then the drain to source voltage or else the drain to drain voltage must be greater than or equal to VGS minus VT. So we are taking the is equal to. So if I substitute in the formula, that is ID is equal to mu naught COX W by L into VGS minus VT into VDS minus VDS square by 2. So if I substitute here in the place of VGS minus VT as a VDD, then we will get the equation of the MOSFET in the saturation current, the equation of the drain current of the MOSFET in saturation region expression will be looks like this. So in this case, mu is the constant. So just leave about that one in the case of scaling parameters. And while coming to the COX, as I told that COX is nothing but a oxide capacitance is a unit area we have to consider, that is epsilon divided by D into W by L into VDD square, and that becomes is equal to epsilon is a constant, so just leave about that one, and 1 divided by D, that means thickness of the silicon dioxide, so 1 by beta, and width is scaled by 1 by alpha, length is also scaled by 1 by alpha, and VDD is a power supply, so we have to scale by 1 divided by beta square. And if we simplify this one, beta into both these two gets cancelled, so 1 into 1 divided by beta square, that becomes is equal to 1 divided by beta. So 1 divided by beta is the correct answer, that is the second option is the correct one for the saturation current of the MOSFET if it is scaled by how much amount? 1 divided by beta amount. And now while coming to the next question, the process which offers the possibility of growing high quality oxides, temperature even lower than those achieved with the high pressure technique. So always the high quality oxides can be obtained with the help of a dry oxidation only. So it is a theory bit, you have to remember that dry oxidations are responsible for the high quality oxides. And coming to the next question, the pull up to pull down ratio for NMOS inverter driven by the another NMOS inverter. So pull up to pull down ratio, generally the pull up ratio can be given as LUP by WP, that means the length by width ratio can be given as a pull up to pull down. So here we are going to see this one. So here it is a NMOS inverter driven by the one more NMOS inverter, and it is a depletion mode NMOS inverter. So as I told that the depletion mode NMOS inverter, that is gate and source, both these two are short circuited. That means this depletion mode NMOS effect is always in the on mode, or else it always in the saturation mode. So if it is in the always saturation mode, then it's a drain current. So here in this case, it is act like a pull-up section, and I mean the depletion mode NMOSFET is acts like a pull-up section, and this is the enhancement mode. This enhancement mode NMOSFET is acts like a pull-down section. So for this pull-up section, if it is in the saturation mode, why it is in the saturation mode? Because the gate and source is a short circuited, so it is continuously in on state. So now in the saturation mode, the MOSFET's equation can be given as K dash. Here the K dash means mu naught COX W by L, this entire thing. So K dash into VDD square by 2, right? So it is the MOSFET's saturation drain current equation. So here I am writing where K dash is nothing but mu naught COX W by L. Okay. So it is a saturation current. In the previous problem, here I told that the drain current, the saturation current equation is mu naught COX W by L into VD square, but here by 2 will be there. Anyhow, in the scaling factors, this by 2 will not responsible. Anyhow, it is a constant, so that's why here it won't play a major role. But anyhow, the formula correction is this one, by 2 will be there. So it's the drain current equation, and where VDD can be taken as VGS minus VT whole square divided by 2 into K dash. And coming to the K dash, I wrote here mu naught COX W suffix PU, that means pull up section divided by L suffix PU, that is pull up section, that means width of the channel and length of the channel, into VGS minus VT whole square by 2. And while coming to this pull down section, NMOSFET is in the enhancement mode, so that's why I wrote the enhancement mode current equation, but here WPD by LPD. Why? Because this enhancement NMOSFET in the pull down section. So now equate both these two and try to get the ZPU by ZPD from this expression. Thank you.